Hello, everybody. Welcome back to class. Thursday, April 2nd. Not sure why I said the date. There's just a few of you here, but we still have a couple minutes before class starts. So you want to just say hi in the chat if you're here, just so I can get a sense of who's here. All right, looks like nope. Oh, Sam, good morning. Good morning, Emma. I hope your sister's joining in with the simultaneous sip again today. Liza, good morning. All right, about another minute or so and we could get started. We're ready. I'm happy to hear that. Good morning, Alex. I just pulled this awesome prank on my calc class. They have a test at 10 o'clock. And so I posted a link on Canvas that says test 2 solutions. Do not open. And it's a link to, that Rick Astley song, Never Gonna Give You Up. So it's an old meme. I don't know if you guys even, you probably know what I'm talking about. It was like popular when I was in high school, but that's the beauty of memes is they never die. Okay. Good morning, Taylor, Ricky, Maddie. Good to see you. All right. Well, it's 9 o'clock. Enough about my pranks. Alex likes it. That's good. We could do the simultaneous sip, and we could get started. So let's do this. All right. You know what to do. Throw me some sips in the chat if you joined in. All right. So we have this last example that we were looking at. So we have this linear transformation, and we want to find a basis B such that the B matrix for T is diagonal. And we have a theorem that says basically what we want to do is we want to diagonalize this matrix. So we want to write, so we'll let A be this matrix. Looks like a lot of people joined in the simultaneous sip today. That's great. So we'll let A be this matrix. We want to write A as P, D, P inverse. Right, because the theorem says that if we take B to be the columns of P, then the B matrix for T is this diagonal matrix. Okay, so that's what the theorem says that we stated at the end of class yesterday. But we already did this, right? This was an example from section 5.3. So we found that P is equal to 1, -1, 1, -2, and D was equal to 5, 0, 0, 3. Okay, and so my question is, how do we finish the problem? We diagonalized it, but how do we get our basis from this information? So D is the B matrix for T. So this is the conclusion of what the theorem said when something holds. Okay, well, you could look back at the theorem and it says when B is just made up of the columns of P. So if our basis is made up of these two vectors, then the B matrix for this transformation, defined by T of x equals A times x, is this diagonal matrix. Okay, so now we could say the theorem that will tell us in general how to find this diagonal matrix, or this the B matrix in general, and then we'll talk about like a quick way to compute this. Okay, so if we have a linear map from Rn to Rn, and it's defined by T of x equals Ax, and B is a basis for Rn, then the B matrix for T is equal to P inverse A P. Okay, so A comes from here, and I'll tell you where P comes from in a second. Where P is the matrix whose columns are the entries of B. Okay, and so if I asked a question that was like, find the B matrix of a transformation, and I gave you the basis, you would just use this fact. Okay, so you'd have to find P inverse. You're already given A, and then P is really easy to compute. So it basically comes down to find the inverse. But there's a shortcut we could use, which I'll write down now, which will make this a little bit easier. So a quick way to compute the B matrix of T is to first compute the product A times P, right? A would be given to us, and P would basically be given to us because we would be given all the basis elements of B. And then row reduce the augmented matrix P AP. Okay, so the first n entries are the columns of P, and the next ones are the columns of AP. I'll put a kind of like a dashed line in the center so we know that they're separated. To what we want the identity on the left-hand side, and what's left over on the right would be P inverse AP. All right, so this is like a quick way to compute the B matrix for T. Okay, so are there any questions? So ask any questions you have about this section, and if you don't have any, we can move on to 5.5. But before we do that, I should make a half announcement or a question for you all. So a few of you have noticed that that I did a study session for my calc class. It was like at 6 o'clock. We just went through a review. We tried to answer as many of the review questions as possible. And so I was thinking we should do the same thing tonight for linear. So how does, let's say, 5 o'clock sound? 6 was a little late for me. So from 5 to 6, we'll just look at the study guide and answer any questions that you have about the study guide. It'll be on YouTube again. So I'll upload it immediately after if you can't make it, but that's kind of the plan. So I see a few yeses. So it seems like a couple of you will at least are interested in this. If you're not interested, that's fine. I'm not taking attendance, obviously. And I'll upload it to YouTube after. Okay. So 5 o'clock tonight, and I'll send out an email just kind of reminding everybody. Okay. Oh, but again, for the test, I'm going to publish it on immediately after class tomorrow, and then you'll have all weekend to work on it. Okay, so it's not like the standard 1 hour test. It's a little bit longer, but it's a little bit longer, but you have way more time. If we cannot make it and have questions, can you email? Yes, yeah. So email me any questions in particular that you want to go over, and we could go over those. Okay. So let's plan on that, 5 o'clock tonight. All right. So now we'll move on to our last section for this test, which is 5.5, complex eigenvalues. Okay, so notice, well, we haven't worked with the characteristic equation, today at all. But what we've seen so far with the characteristic equation is that the solutions have always been, lambda equals some number, and it's a real number. But as you've seen in like an Algebra 2 class or your pre-calc class, when you set a polynomial equal to 0, sometimes you get solutions that are not real numbers, right? You'd have like complex numbers. And that's possible when we're dealing with these matrices. So we're going to take a look at some examples of when these complex numbers appear and how to deal with them. Okay, so that's kind of the big idea. So the complex eigenvalues, this section shows that if the characteristic equation of a real matrix A has some complex roots then these roots provide some information about A. But the key is we're gonna say that A doesn't act on Rn anymore. We'll say it acts on Cn, which is lists of complex numbers. Okay, so just in the chat, have you all seen complex numbers before, or at least is this a term that is a little bit familiar to you? The idea of a complex number, right? It's like maybe you heard the word imaginary, which is a terrible term. Yeah, so complex or imaginary numbers hopefully are a little bit familiar to you. If not, we'll go through a little bit of the algebra behind it. Taylor says yes. We're not going to go through a lot of the details of complex numbers because we're not terribly interested in them, but there's a few tricks that we're going to have to look at. Okay, so let's look at an example. Okay, so suppose we have this matrix, 0, 1, minus 1, 0. So then the linear transformation that sends x to ax rotates the plane. Okay, when we first looked at linear transformations, we saw that there was a rotation map that had sines and cosines in it. So this was like when you plugged in theta equals pi over 2, you would get this matrix. So it rotates the plane by 90 degrees. So rotates R2 counterclockwise through a quarter turn. Okay, that's not terribly important. But what is important is, well, remember our initial definition of an eigenvalue. It was something that just gets stretched when you multiply by a matrix. Or an eigenvector, sorry. An eigenvector gets stretched when you multiply by a matrix. It doesn't get rotated at all. This matrix, when you multiply a vector by it, rotates every matrix by 90 degrees. Okay, so other than the origin, every vector is rotated. It's not stretched, it's just rotated. So there's no real eigenvectors here. So no. And we'll see this when we look at the characteristic polynomial. There'll be no real solutions. So no non-zero vector is mapped to a scalar multiple of itself. So A has right? Because just recall what it means to be an eigenvector. That means if you multiply that eigenvector by A, you're just stretching it by some factor, and that factor is the eigenvalue. It's not quite the end of the sentence, and no real eigenvalues. So let's take a look. So what's the characteristic of equation of A? How would we find the characteristic equation of this matrix, or of any matrix? Okay, so how do we get this? And if you're unsure, just maybe, I don't know, put a confused faced emoji or a question mark, or just some sort of feedback so I can make sure you're all listening at least. Thank you, Taylor. I appreciate the confidence, I mean the courage. The characteristic equation, remember? So that was the determinant of A minus lambda I equals 0, right? Does this look familiar? Hopefully. Maybe we forgot that it had the name, the characteristic equation. But yeah, so let's work out what A minus lambda I is, compute its determinant, and then set it equal to 0 and see what we get. So A minus lambda I is the matrix minus lambda, minus 1, 1, minus lambda. And so we want to find its determinant. So it's lambda squared minus negative 1. So lambda squared plus 1, and we want to set it equal to 0 and solve this equation. Well, lambda squared plus 1 equals 0 has no real solutions. The only solutions are complex, right? So the solutions to this are lambda equals I, and lambda equals negative I, where I is the square root of negative 1. So the eigenvalues of this matrix are complex. And one can check that if you take the matrix A and multiply it to the vector 1 minus I, you would get I times 1 minus I. And you could also check that if you take our matrix A and multiply it to the vector minus I1, you would get minus I times that same vector. Okay, and now where did these come from? We don't know yet. But it appears that we have some sort of eigenvector that lives, in C2 as opposed to R2. The entries are complex numbers. Maybe 1 is not, but it technically is. It's 1 plus 0i. But the second entry is most definitely a complex number. So thus, I and negative I are eigenvalues with 1, negative I, negative I1 as eigenvectors. And so the question is, how do we find these complex eigenvectors? Okay, and I don't expect you to know this answer. That's really, I'm writing it as this is what we're going to do now. So I'll give you, 30 seconds or so to kind of catch up with the notes. And then we'll discuss how to find complex eigenvectors. And we'll discuss it through an example. So it should be not very abstract. All right, feel free to ask any questions you have along the way. Trying to fix this this glare we have going on. This helped. Might have made it worse. Okay, so if there's no questions, we could keep going. Okay, so I'm going to write out a matrix, and I'm going to ask you to find its characteristic equation. And then, so I'll give you about a minute to do that, and then I'll catch up, and then we'll continue from there. So don't even bother solving the characteristic equation, just find it. So let A equal the matrix 1, 1, minus 2, 3. So I want you to find the characteristic equation right now, and I'll finish writing this question. Find the eigenvalues of A. And a basis for each eigenspace. Okay, so try to find the characteristic equation, and then if you get it, feel free to type it into the chat. You could use the letter X instead of lambda, unless for some strange reason you have like the Greek letters on your keyboard, then use lambda, but X is fine. Yeah, Taylor, that looks good. So if you could get the characteristic equation, then try to solve it. But I'll do that or I'll talk through it in a minute. Yeah, so we want to find A minus lambda I. So for all these eigenvector type questions, if you're not given the eigenvalues, the way you find it is using the determinant of a minus lambda I. And now let's find its determinant and set it equal to 0. So that's lambda squared minus 4 lambda plus 5 equals 0. Okay, now my question for you is, how do we solve this? So how do we solve this characteristic equation? Yeah, the quadratic formula is probably our best option. Completing the square also would work, but quadratic formula is a little bit nicer. All right, so that's saying lambda equals negative b, so 4 plus or minus the square root of 4 squared minus 4 times 1 times 5 all over 2. So this is 4 plus or minus 16 minus 20 is this. So you get 4 plus or minus 2i over 2, which is equal to 2 plus or minus I. So just a show of emojis, or I don't know how to communicate here. Are we good with solving this quadratic formula and getting 2 plus or minus I as our solution? I could go over it again if you need me to. But okay, I see a couple of thumbs up. The rock on thing, whatever that is. So now we want to find the eigenvalues here. Lambda, so there's 2 eigenvalues. Lambda equals 2 plus I, and lambda equals 2 minus I. And now we want to find a basis for each of the eigenspaces. Okay, so how do we do that? This is the same as finding a basis for the eigenspace for just a real eigenvalue, except we're going to have some complex numbers bouncing around. So let's start with so we'll find a basis for the lambda equals 2 minus I eigenspace. And then we'll move on to the other one. Okay, so the matrix A minus 2 minus so the matrix A minus 2 minus I times lambda looks like, well, you're just replacing lambdas with 2 minus I. Okay, so that's going to be negative 1 plus I, negative 2, 1, and 1 plus I. And yeah, I guess we'll have a row of zeros. Well, we want to now we want to find the null space of this matrix. So we'll take the same matrix, put a row of zeros at the end, and reduce this until we could get reduced row echelon form here, and then we'll be able to read off our solutions. Okay, so how do we deal with the complex number? How do we deal with this -1 plus I? Does anybody have any guesses? And I think it will truly be a guess. And even just question mark, like if you're not sure, just question marks would be appreciated also. Yeah, so we're gonna try to make it equal to, try to make it equal to I instead of 1 like normal. That's a good idea. We're actually gonna try to make it equal to 1. And there's like a little bit of a trick that we have to pull here to make this work. And so now, I mean, if you go on and take a class where you study the complex numbers, this will be like second nature to you, but for now, it's just kind of like a little bit of a trick. What we're gonna do is we're gonna take, so we wanna get a 1 in this top left entry. Sure, we could just switch the rows. Yeah, Alex, exactly. Complex conjugate. Taylor, you're on the right track. Squaring it is gonna, there's still gonna be some i's. If we multiply by the complex conjugate, we'll get a real entry in our in this top left corner. So let's take row 1 and multiply by the complex conjugate, which is, all right, let's write this as 1 minus. Sorry, I wrote this wrong. This is -1 plus I. So the complex conjugate is -1 minus I. Okay, so we're taking row 1 and we're multiplying it by -1 minus I. And the idea here is, well, -1 plus I times -1 minus I is equal to 1 squared minus I squared, which is 2. Right? And there's no complex parts of this anymore. So this complex conjugate has this beautiful power or property that when you multiply a complex number times its complex conjugate, you just get a real number. And so our matrix becomes 2, -2 times -1 minus I, 0, 1, 1 plus I, 0. And I notice this -2, this negative I could factor in. And look, the top row is twice the second row. So if we just add 2 or -2 times this row to this row and then switch the order, we'll get 1, 1 plus I, 0, and then all zeros. Okay, and now we can solve this. This row tells us that x1 plus 1 plus I times x2 equals 0. x2 and our eigenvector x is equal to -1 plus I x2, x2,
Pull out the x2, and we get -1 minus I and 1. Okay, so this vector here is the basis for our eigenspace corresponding to lambda equals 2 minus I. Okay, before we move on to the next part, which is doing the same thing but for lambda equals 2 plus I, feel free to ask any questions, and also maybe get started on this part. So the basis would just be this vector. Okay, so now we'll repeat this with basis for lambda equals 2 plus I eigenspace. All right, so I'll give you a minute to try to work this out or get started at least. But please ask any questions you have. So this multiplying by a complex conjugate, it turns out, is like basically the same thing as dividing by. Typically, we would have said, oh, let's just divide by -1 plus I to turn this into a 1. And it turns out that the way you divide by a complex number is you do some scalar multiple of the complex conjugate. So that's kind of a neat property of complex numbers. All right, but if there's no questions, we could just keep going on this one. So we need to find the matrix. Oh, this should be an I here, by the way. A times 2 plus I times the identity matrix. And we'll do the same thing, put it in an augmented matrix, row reduce it until we could get a solution. Okay, so my question is, what is the complex conjugate? What is the complex conjugate of -1 minus I? Yeah, exactly. The way you get a complex conjugate is you keep the real part the same, and you just switch the sign of the imaginary part, if you will. So we started with -1 minus I. The complex conjugate is -1 plus I. So this product, again, will be 2. And this would be 2 minus 2I. Okay, and again, you can see row 1 is twice row 2, so we could get rid of it. And then this says that x1 plus 1 minus I, x2 equals 0. And so x1 equals -1 minus I, x2. And we have x is equal to minus 1 plus I times x2, x2. Which works out to x2 times negative 1 plus I, 1. And so the basis for the eigenspace is just this vector. Okay, now something to observe, and maybe this is always going to be the case. We'll see tomorrow. The eigenvalues are complex conjugates of each other, right? So we had 2 plus I, 2 minus I. Those are the complex conjugates. And the eigenvectors, the entries of them, are complex conjugates of each other. All right, we have negative 1 minus I. Here we have negative 1 plus I. And it turns out that's always going to happen, which is nice. It'll save us a lot of time. So we're going to have a theorem tomorrow that says, well, we don't even have to do the second part of the problem. Once we found the eigenspace for lambda equals 2 minus I, we could automatically find the one for a basis for lambda equals 2 plus I. Okay, so let's just state a quick definition, and that'll be a good place to end. So please ask any questions you have, and they could be about the test if you're wondering, like about, just if you have any questions about anything. It could be, it doesn't even have to be about math. It's just whatever you're interested in. Ask me anything, as they say. So let X be a vector in Cn. The complex conjugate of X is the vector X bar. Okay, the notation is a little bit rough for this, but you take our vector X and you put a bar over it. It's better in the book when they do bold because it's just bold with a bar, but since I can't draw in bold, this is what we got. So it's the vector X bar in Cn, whose entries are the complex conjugates of the entries of X. Okay, so just a quick example so you can see what we're talking about here. So for example, if X is the vector, let's say 1 minus I, 3, and 5 plus 4I, what is its complex conjugate? Well, to find the complex conjugate, we just want to take the complex conjugate of each of the components. So the complex conjugate of 1 minus I is 1 plus I. Yeah, exactly, Taylor. The complex conjugate of 3, well, there's no complex component of 3, so it just stays the same. and the complex conjugate of 5 plus 4i is 5 minus 4i. Okay, and we'll see that these conjugates play a big role in finding the eigenspaces when our eigenvalues are complex numbers. Okay, so we'll pick up with this tomorrow. The plan for tomorrow is we'll finish this up. That will take 10 minutes, maybe a little bit longer. And then the final 30 minutes or 40 minutes, we'll just go over some more review problems. So tonight at 5, we'll do review problems. Half of tomorrow, we'll finish up complex conjugates. And then we could spend half hour or so tomorrow working on review problems. Okay. So the important things, make sure to hit the like button before you leave. It's going to help us get to 1,000 subscribers. Take a look at the review questions I asked, or I gave you. What time of, and yeah, just let me know if you have any questions. What time of the day on Monday is the exam due? That is a good question. I'll see if I ever put it in an email, but if not, we could plan on 9 a.m. Seems fair. Yeah, it'll be in the morning, but yeah, I think I could give you a little bit of time Monday morning to work on it as well. But I would plan on just trying to crank it through on Saturday and Sunday. It really should not take you 2 days. I do not want people submitting it late, though. Oh my gosh, I swear. So if there's a deadline, let's say the deadline's 9 a.m., try to get it in the night before so we don't have to worry about handing it in late. Okay, well, that's all I got. So email me any questions. Hit the like button before you leave. What is the first section of the test? So, oh yeah, so the test covers, and I'll put this in the email, what we did in chapter 3, so determinants. Chapter 4, which is all the theoretical stuff. And then chapter 5, which is eigenvalues. Ben says, love the stream, smashing that like button. Good. That's a good example for your classmates. But yeah, so Liza, chapter 3, determinants, is the first section. Okay. If there's no other questions, it seems like our live chat is getting flooded with the online trolls. I'm going to end the stream. Okay. Bye-bye.